All right, thanks everyone, and a special thank you to the organizers. Today I'm going to be presenting mostly work from my PhD. This is kind of like a little slice of the stuff that I did for my dissertation, and I'll talk a little bit at the end about what I've been up to recently. But today I'm going to be talking to you about sexual behavior in jumping spiders, and also a little bit of thermal physiology, which will give some of the context for the results that I found. So to start off, there we go. The driving question of my dissertation work was, how do animals deal with temperature? And we kind of have this intuitive sense of temperature being important because we know that extreme temperatures in either direction can be challenging for us. But what's sometimes a little bit more difficult to conceptualize is that for animals that can't regulate their own body temperature using their metabolism, this other effect of temperature, the fact that it directly alters the rate of chemical reactions, can be even more important. So for these animals, instead of feeling hot or feeling cold, they actually speed up and slow down. And this extends to things like reptiles, amphibians, fish, and pretty much all invertebrates as well. So if you want to study temperature and study the different varying complex effects of it, a good place to do this is the desert, because we know in our heads the desert is a place that is hot. And this is where I work. So this is southern Arizona in the US. It's right close to the US-Mexico border. And I work in this mountain range here, the Santa Rita mountain range. And indeed, this is a hot place to be. You will frequently see habitats that look like this, and you'll see field biologists that look like this at the end of a long hot day. But another thing that's kind of interesting is sometimes you see scenes that look more like this. So really, when we say the desert is hot, it's slightly more accurate to say the desert is variable. The desert can be extremely variable when it comes to temperature, not only on a seasonal basis, but on a daily and even hourly basis, as you can see here. So this is a few weeks in April, and you can see the solid line is the mean daily temperature. But look at all that variation. The pink area represents minimum and maximum temperature, and that is a gigantic range that these animals are having to experience. So if we want to study animals dealing with temperature in the desert, who do we want to study? And I kind of fell upon Habronattus for a variety of reasons. Just a few little factoids about these adorable little spiders. There's about 110 species. I think that might actually be closer to 120 now, more are being described all the time. They're hyper diverse and recently diverged. The group itself is less than 2 million years old. There's a diversity hotspot in the southwestern United States. They are a North American group, but southwestern United States, there's tons of different species. They're highly dimorphic, related to size and their colors and sexual ornaments. And also they can be habitat generalists or specialists. And this kind of became important when I was interested more in kind of the ecology of the animals. And finally, and this is something that is a little bit easy to forget when you're looking at these gorgeous zoomed up pictures of their faces, they're quite small. They only range from about 5 to 30 milligrams as adults. And this is a particularly large male in my hand. So they're quite tiny little guys. And the fact that they're small isn't just striking visually, but it also means that they equilibrate really quickly to whatever temperature regime they happen to be in. So the star of our show today is Hibernatus clypeatus, and I selected them for a variety of reasons. They live in the desert, and also we had them in the lab when I started my PhD, which, as is often the case, definitely influenced my choice as well. So question for my dissertation work, how do desert animals interact with temperature? And I kind of thought of this as sort of overlapping concentric circles of interaction. So the way I structured it is something like this. So they can have, temperature can have effects on the animal's physiology, on their interactions with the physical environment, their intraspecific interactions, and then more landscape level processes. Don't worry, I'm not going through all of this today because it is too much. But I'm going to focus on two aspects. One is going to be their thermal physiology and also their intraspecific behaviors. And the reason why I chose these two is because sexual behavior is definitely most relevant for the topics that we're all interested in biotremology. And I think the thermal physiology kind of puts that in some nice context. So let's start with the physiology. How are physiological processes influenced by temperature in these animals? And the way that I structured this part of the study is by using something called the thermal performance curve. And it's really quite a powerful tool. The way it works is you have temperature on the x-axis, performance on the y-axis. Performance is intentionally broad. You can put anything there you want. And it basically shows how the animal performs at different temperatures. And what I really like about this conceptualization of thermal physiology is it lets you ask some very specific questions about how the animals interact with temperature. For instance, what are the thermal limits? So at what cold and hot limits do animals stop being able to perform, stop being able to function? How big is their temperature range? What is the breadth between the coldest and hottest that they can handle? What's their preference? So if you put an animal in a thermal gradient, where do they like to sit on this curve? And then finally, you can take performance and you can put anything there. So in my case, I use respiration and locomotion, but you can do growth rate, eating rate, whatever you want. So I'll just give you a little quick indication of how I studied this, the methods that I used to assess thermal minimum and maximum. I made this thermal tolerance rig with little chambers, and you put a spider in each chamber. And this whole thing is in an incubator, and you flip the whole thing over as the temperature is increasing or decreasing every couple minutes. And then the temperature at which the spiders can no longer right themselves is that thermal limit, either the hot or the cold. For a thermal preference, we made a thermal gradient with this metallic grid with different lanes, and then we applied heat to one end and put the whole thing in a cold room. So you get this nice thermal gradient from 60 down to about 15. To measure respiration across temperatures, we use some respirometry methods where we put spiders in this little airtight syringe and then incubated them at a given temperature for a certain period of time, and then measured the quantity of gases that are accumulated. And then finally, we measured locomotion across temperatures. And because jumping spiders like to jump, we measured jumping in this case. So we just measured some characteristics of their jumps at different temperatures. All right, what did we find? First of all, thermal tolerance. Gosh, these spiders have a high thermal maximum. They can really withstand very high temperatures, which kind of goes back to, yes, the desert does in fact get quite hot. Conversely, these spiders don't handle cold very well. In fact, if this particular species was where I'm at now in Ontario, Canada, they would be pretty knocked out most of the year. Another thing that's interesting to note is even though their cold tolerance isn't very good, their thermal breadth is still pretty extreme. So there's a very wide range of temperatures that they can withstand. Next thing, looking at thermal preference. This is just looking at the preferred temperature on the X and the number of individuals on the Y. It's a histogram. They have pretty strong thermal preferences. So 50% of individuals are in this green bar here, right around 40 degrees, just a little bit below. And I'm going to be putting these green preference bars on other plots in the future to kind of give you a sense of where they prefer to be. And then one thing that's kind of interesting that popped out is when we divided the preference by sex, we noticed that females actually have lower temperature preferences than males. So males like to be warmer than females. And this is something just to kind of keep in the back of your head as we move from the physiology end of things and into behavior. Respiration, so again, our thermal performance curve, we put respiration on the y-axis, and we found that indeed metabolism increases with temperature. That green bar is where they prefer to be. And then looking at locomotion, we see a bit of a plateau right around their preferred range, which kind of makes sense. They would seem to prefer to be kind of where their maximum is going to be. And this is just jump distance and then maximum jump velocity. Okay, so looking at performance altogether, jumping is less temperature sensitive than respiration, which is kind of interesting. So metabolic costs accumulate faster than performance will increase. And then just to summarize the physiology section, they have high heat tolerance, not so much in terms of cold. They have a very large thermal breadth. This is approaching some of the higher thermal breadths that have been found for invertebrates. Males prefer higher temperatures than females, and also they have very specific preference ranges, despite this very wide range that they can live in. And then locomotion and respiration both increase with temperature. They can maintain very high performance at quite high temperatures. Okay, so moving on from the thermal physiology, we're going to ask about intrasexual interactions. And this almost ends up sounding a little bit euphemistic because when I say interspecific interactions, what I mean is sexual interactions. So these individuals use intrasexual displays in order to entice the other to mate. And I'll just explain real quickly how this works in Hibernatus. So intrasexual communication works something like this in these guys. So you have a courter, one who performs the courtship behavior, and you have a chooser, one who observes the signals and then makes a mating choice. And the courter produces a signal. So this signal could be just about anything. It could be a sight, a sound, a smell. So for instance, this individual could have a bright colored patch, and then the chooser could see it, beamed into the chooser's eyes, and then make a decision about whether to mate with this courter. Or it could be a sound, or in the case of this spider's, a vibratory signal. And then the chooser decides whether or not to mate with the courter based on this signal. So yes, mate, or no, do not mate. And then just as a note, in Hibernatus, as far as we know, males are always the ones that are the courter and females are the chooser. So I'm going to be using male and female in place of courter chooser here, but just know that the males are always the ones doing the courtship. And then just as an indication of what those vibratory displays are like, they do visual stuff too, but I'm going to mostly focus on vibratory. This is a 1-minute section of a Habronattus clypeatus vibratory song. And if you're familiar with Damien's work, you'd know that they have this very complex hierarchical structure to their songs. So they have kind of these repeated motifs, and that can be considered analogous to something like a musical composition or a symphony. And then within those motifs, there are individual vibratory elements. So you can think of them as like words or sounds. And those 3 elements are, and I'll play the sound so you can hear it, are scrapes, thumps, and buzzes. The scrapes and thumps are stridulatory, and the buzzes are tremulatory, where they just kind of uncouple the 2 parts of their body and vibrate it back and forth. And I should mention that all of the sound is produced by a scraper and a file on the back of the cephalothorax and the front of the abdomen. So they're rubbing their body parts together. Can you hear it now?
Fine.
Okay, good. And then we did an experiment to basically see how temperature affects sexual signaling. And this has been done in a variety of different species. We already know that temperature does, in fact, affect signaling in a variety of different systems. This was done at its most earliest in the 70s with frogs. It's also been done with crickets. For instance, the thermometer crickets, that you can tell what the temperature is outside based on their rate of calling. And there's been other work done in wolf spiders and fruit flies, and even more since then. So there's been a fair bit of work done in this. But the reason why I was interested in doing this in Hibernatus is because they have a very complex signal. It's not just a simple repeated series of chirps. It's something a little bit more to it. So my question was, how does temperature influence both male signals and also female mate choice? We set up an experiment where we used a very sophisticated method of taking a terracotta planting platter, and we put it on an electric pancake griddle and warmed it up. And then we put a male and a female on there and recorded what the male did. And then we took an identical platter, put it in the freezer to cool it down, and then listened to what the male did in that case. And then the females were allowed to make choices. They either chose to copulate with the male, accept the male, or reject the male. So we ran a series of experiments to determine, and then we also recorded the male songs as well, so we could get a sense of the male signals and the female choice. So some results first on the male end of things. This is a plot of just one aspect. This is the fundamental frequency of the male buzzes. Each individual is represented 3 times on this plot. The cold, the room temperature, and the warm treatment. Temperature is on the X, and then the frequency is on the Y. So I'll play a sound of what an example buzz sounds like in the cold, room temperature, and hot from the same individual. This is a repeated measures. So at the cold temperature, it sounds something like this. At the room temperature, it sounded like this. And then at the warm temperature. So it does change a fair bit. And note this green bar is actually where the males like to be. So they actually like to be in the region where they're producing the highest frequency sounds. And then looking at female choice patterns, they also change as well. Females are more likely to mate in the high temperature, as we have temperature on the X and mating rate on the Y. And then just to remind you again of where the different sexes like to be, males like to be at higher temperatures and females like to be at lower temperatures. So there's this kind of interesting complex interplay going on where the males like to be where they're going to have the highest mating success, whereas females like to be where in an area where they're exerting more choice, where they're being choosier. So this is kind of an interesting complexity here. And there's a little bit more that I want to add to this story. I actually ran a second set of experiments because this one, we actually assessed male signals and female choice separately in 2 different experiments. And because of that, we were able to measure female choice, but not female preference. So in this experiment, we measured everything together. And then as part of that, we used some dimensionality reduction to take the male signals and turn them into principal components. PC1 was aspects of vibratory courtship. PC2 is visual courtship, dealing with mean aspects of the individual components. And then PC3 was overall rates and durations of the visual display. And there's a lot of interesting stuff that kind of fell out of this, but I just want to tell you one little mini story from this, and that is to do with PC3. So this is overall rates and durations of displays. So lower values of this PC is shorter displays, and higher values is longer displays. And what we found is that looking at these aspects, they don't change across temperature treatments. We only use room temperature and hot here because the mating rates for cold was essentially nothing. So for this experiment, we zoomed in on just room temperature and hot. And the aspects of visual courtship contained in PC3 don't change much. However, when you look at female preference for these aspects for PC3, so if we have PC3 on the x-axis and then probability of copulation, you'll see that in the room temperature, there's no difference. So females don't really have differential preference for different aspects of this PC. However, when you look in the hot, they're actually more likely to mate with males, significantly more likely to mate with males when males perform shorter displays. So there's something about this hot temperature where females are kind of telling the males, you better hurry things up. They don't like to mate with males that do overly long displays. So that's kind of an interesting thing that popped out of that. And then to summarize the section here, male signal characteristics increase with temperature, and then female receptivity changes with temperature, as does their preference. And there's some really interesting potential for really complex interplay between courtship, temperature preference, environmental temperature, all sorts of things. And then for some future directions, I'd like to disentangle male and female body temperatures. And I'm doing this with this device that's been in the works for a while, where we can shine a laser on the male or the female to just warm one of them up. So we can tell if the female is making choices based on properties of the signal itself or making choices based on her own body temperature. Okay, so to summarize, how do desert animals interact with temperature? We learned that from the physiology, they perform well at high temperatures. So they're definitely high temperature specialists. And then for their sexual behavior, signaling and receptivity both change, and these changes are complex and nonlinear. There's really a lot going on, and there's a lot more experiments that can be done to kind of tease this apart. And before I finish everything off, I realized that I'm doing some pretty different stuff now. So I just wanted to give you guys a little preview of what's been happening during my postdoc. So for starters, I have moved a bit over to the dark side from biotremology into acoustics, and I'm doing some modeling of cricket song. So doing some looking at different frequencies and sizes of wings and seeing how that affects sound fields using finite element modeling, and also doing a bit more mechanics-y type stuff and actually quantifying the mechanics of spider jumping. And that study recently was published. So getting a little more mechanics-y, a little more acoustics-y, but still doing a lot with Hibernatus and definitely still interested in the questions about temperature and their interactions with it. So just to acknowledge everyone in my PhD lab, my funding sources, my current lab, Natasha, and all of my other lab mates who are here today. And at that point, I would be happy to take questions.